So what we're going to start off discussing today is we're going to start off discussing planes. So a plane is a flat, uniformly flat shape in three dimensions that kind of stretches out infinitely far in each direction. And they have equations that we can use to describe them that look very much like the equation for a line looks like in 2D. It's ax plus by plus cz plus d is equal to 0 for some random real numbers a, b, c, and d. So 3x plus 2y plus 5 is equal to 0. That could be the equation for a plane. Or sometimes you see people write it with the constant on the other side, and that's fine. It describes the same thing, but for convenience we often move everything over to one side, like so. Now, to find the equation for a plane, we need a couple of pieces of data, just like we needed data to parameterize a line. And the two things we usually need are a point that we know is on the plane somewhere, and we also need a normal vector. Now, when we were doing lines, we needed a direction vector that pointed in the same direction as the line. And the normal vector kind of is the opposite. Instead of asking for a vector that points in the same direction, we're asking for a vector that's perpendicular. It's at 90 degrees to the surface of the plane, like that. And if we have those two pieces of data, then the equation looks like this. It's 0 is equal to the normal vector dotted with direction vector minus p. So here, a couple of things to write down. This is the dot product. We add up the products of all of the things. This is the thing from classical vector geometry. This here again, x is shorthand for x comma y comma z, like so. N is our normal vector and p is our point. And geometrically this has a particular meaning. If I have some other random point q that's floating out here, and I want to know if q is on the plane, here's how I find out. I draw a vector from p to q. That's this vector q minus p that we see in the equation. And then I take the dot product. And the dot product geometrically tells me something specific. The dot product is always the length of the normal times the length of this vector q minus p times the cosine of the angle theta that they make between them. And if my point q is going to be on the plane as opposed to off it, it's supposed to be at 90 degrees. The angle that they make is supposed to be a right angle. And the only way that happens is if the angle is 90 degrees or the cosine of the angle is equal to 0. And so setting this equal to 0, setting this dot product equal to 0 is the same as asking for that angle to be 90 degrees. And the equation for the plane is the convenient property that it's a little bit reversible. So if we have the equation for the plane and we want to go backwards and figure out a normal vector, that's actually very straightforward. If we have an equation for a plane that looks like the left-hand side here, we could just pluck off the coefficients of x and y and z and stick them in a row vector in that order, and that gives us a normal vector to the plane. It's nice that you can go so cleanly between those two procedures. On the other hand, finding a specific point is a little bit more difficult. What we usually do is we choose random values for two of the variables and then we solve for the third. So for example, because we are lazy, we could go over here and say, okay, if I want to know a point on this plane, I can plug in x is equal to 0 and y is equal to 0, and that leaves me trying to solve for 2z plus 4 is equal to 0 in this equation. That gives me z is equal to minus 2. And so this point then is one of the points on the plane. So saying this, I have to be reminded that the last letter of the alphabet that I say might be different than the last letter of the alphabet that you say.